Welcome, everyone. Today we'll do 3.3 and we'll start 3.4. Homework is due tomorrow. Homework help the usual times. I can never seem to remember it, but I emailed that out, so hopefully you should have that. I'll be available 2 to 3 tomorrow. OK, so next 2 weeks are a little bit unusual in terms of the schedule. So we'll have a class on Monday. We'll finish 3.4. And then Monday evening, Monday night, I'm not sure exactly when, I'll send out the midterm, which is open notes and untimed, essentially. And that'll probably be due Wednesday morning. If that doesn't work for you with your work schedule, that's OK. Just let me know. It will be easy to figure out some alternative. Thursday, there's no class because of the SHE conference. So the next class after that will be Monday, and then Thursday, and then Friday. So this is week 5, 6, 7. Friday of week 7, there'll be a long homework due, because it will cover sort of like 3 classes worth of material instead of 2 classes worth of material. But you'll have the long weekend. I'll post that, and we'll have gotten through. Certainly, you'll be able to start all of 3.3 and all of 3.4. You can get a big start on that over the weekend. So that's the schedule coming up. Are there questions on that?
Will there be help for the
Oh yeah, there'll definitely be help then. And over the week, I mean, I'll be around over the weekend. I don't know about the other TAs, but if like you're totally, Thursday or Friday of the SHE conference, you're totally flummoxed by calculus, we'll be around. Yep. So yeah, no need to worry. All right. So let's see. The first thing I want to do is mention a sort of notational thing about homework, and then we'll launch into 3.3. So for homework, you often might be having to take the derivative of functions like this, x to the minus 2. And then you think, or actually, sorry, let me start by writing it like this. 1 over x to the minus 2. And you'll say, oh, wait, I want to bring the exponent plus. I want to bring the exponent upstairs. I'm going to write it like that. And then you say, all right, now that I've got this in the form that I can use the power rule, I'll do that. And you're just kind of working along. Don't do this, please. OK, so the problem is, all right, so this equals that. But this does not equal that. You actually did something to that changed the value of it. You took the derivative when you did this. But this is true because this does equal that. So for the homework, like in 3.1 and 3.2, there's like a long string of odd problems where you're just practicing that algebra, and you kind of get in a rhythm. But it's useful to remember you're doing 2 things. You're simplifying, or you're taking the derivative. And those are separate things. And when you simplify, you're preserving an equality. When you take a derivative, you're turning a function into a new function, and it's not an equality anymore. So some of that is you shouldn't write it this way because it's wrong. But also, if you're careful about how you're writing it, then you'll keep those two things separate in your head. So so y equals x to the minus 2. Y prime equals minus 2x to the minus 3 equals 2. So just make it clear when you're working with a function and when you're working with a derivative. I mean, it's not a huge issue, but lots of people kind of just get in a rhythm and end up writing all sorts of equations that are technically wrong. It's not a big deal because I know you're thinking of it right, but it's always good to be clear. Does that make sense? All right. So what I want to do now is start 3.3. And so chapter 3 in general is about shortcuts. Just quick, concise, ways to find derivatives of important functions. And we know now how to do power functions and exponential functions, the most basic type of functions out there. 3.3 will also lead us towards a nice rule, but it's going to take a little bit more development than these two. So I'm going to try to sort of lead you through why the rule we're about to do is true, and then you'll do a bunch of examples. So I'm going to guess I'm going to probably talk for 10 or 15 minutes. Again, just so you sort of know how to ration out attention. So hang on for 10 or 15 minutes, and then you can stop listening and do your own thing. All right. So 3.3 is about the product rule. And it applies to functions that are like this. So this was one of the exercises from last time. The answer was, huh? Do you remember that one? That was a rule we hadn't learned yet. And I said, well, because it's two functions multiplied together, now we're going to learn how to deal with these functions that are multiplied together. So an example might be, like if f of x was x squared 3 to the x. So those are two functions, and you know how to take the derivative of x squared. You know how to take the derivative of 3 to the x, but you don't know what happens when they're multiplied together. But we're going to figure that out together now. And I'm going to not do a formal proof, but try to justify this rule with a picture and a story. We'll see how this goes. So we'll start. Imagine you're opening a store, some sort of business. And so what should the store be? Sort of like comedic improv or Mad Libs. A store, what type of business would you like to go into?
Candy store.
Candy store. What do people think? Candy store? Candy store. All right, there's consensus. Excellent. Well done. All right, so you're going to go into business selling candy. And so this might be the amount of candy. And then this would be the cost, or I'll call it cost per candy. We're not going to worry about grammar. We're going to have enough other things to worry about. So the idea is that this would be like how much money, your revenue. And you're selling some amount of candy, and you're selling it for some price. Per pound, per whatever unit you're selling it by, per item. So anytime you have two numbers multiplied together, you could think of that as an area. So I'm going to do this here. Let's see. And call this h of x, g of x, and then this is f of x. Because the area of a rectangle is base times height, and if the base is g and the height is h, then that's the area. So just geometrically, the amount of money at time x, maybe I should have done this with t instead of x, but it doesn't matter. At x, the amount of money you're getting in is represented by this area. All right, so we're interested in the derivative of this sort of thing. And what do we know? This is one of these difference quotients. Probably didn't even need to write the difference quotient down. The main thing that I want to remind you of is that this is just change in f over change in x. That's what derivative is. It tells you how f changes when x changes. The only thing now is f has these two parts to it instead of one. All right. So now let's imagine something changes. X, there's a different x. Maybe this is t, and a little while later, things are going well, and it turns out you're selling more candy, And maybe because you've gotten everybody hooked on your candy, you can charge more for it. Right? That's a good strategy. Get people addicted to your product, then raise the prices. I mean, it's a good in one sense of the word, good. In any event, for whatever reason, you realize you can sell more candy and you can charge more. So this is exciting. You've got G has increased and H has increased. All right, so let's say G increases by an amount delta G. That's more, you're selling more candy. Word's gotten out. And you're charging more because everybody's hooked on your product. So now, right, cost per candy has gone up. And now you have more revenue. And notice that you have more revenue for two reasons. You're selling more and you're charging more. OK, so delta F, that's your increase in revenue, how much the function itself goes up. That's going to increase because of this area here. Do I have any more colors? Yes. Let's see. OK, so the extra that you have is due to this orange rectangle. And what's the formula for the orange rectangle? It's base times height. So that's going to be G times delta H. So who else uses colored chalk in this room? Where does it go? I usually assume that it's only Davis who uses colored chalk. But apparently somebody else does. OK. So this is that. Then you also get more because you're selling more of it. So that's this rectangle. And what's the area of that rectangle? H delta G. Really delta G H. OK. All right. So are we doing OK so far? All right. So good, because now I have to do something that you're maybe not going to like as much, which is I'm going to ignore. You're probably wondering, but wait, there's this little square here. I'm going to ignore that. And the reason I'm going to ignore that is that we're going to imagine that these are actually really tiny changes. So just tiny, tiny little slivers. So this is also a tiny little sliver. So then this is tiny little sliver by a tiny little sliver. It's really tiny. And it's really small compared to these two. Did you buy that? OK. It's all right. You can say no. All right. Let's see. So let me. And we're going to ignore because so small. All right. Let me go forward a step in the argument and then try to go back and justify this assertion. I mean, I haven't really, other than saying it's so small, I haven't really justified it, other than like writing in orange on the board, which is a form of authority, but not really justification. All right, so we're interested ultimately in this. We want to know the derivative of f. How does f change when we've got these two things going on? So delta f over delta x. All right, I know what delta f is. That's this. G delta h plus delta g h. Sure, yep. And then I'm going to just divide by this. All right. So now I've got g times delta h over delta x. And delta h over delta x, what's another word for that? If these deltas get really small? Well, if f prime is how f changes with x, this is how h changes with x. So that's just the derivative of h. Let me OK, so this was just fractions. No calculus here. Just taking a fraction and splitting it into two. And then what I'm claiming is that this term is h prime. This term is g prime. So f prime equals g h prime plus g prime h. So this is the product rule. Let me try to give another justification for why we can ignore this little square. And then, well, you can still decide if you believe it or not, but I'll probably be out of justifications at that point. So do you remember when we did, by hand, using difference quotients, calculated the derivative of x squared? We had to FOIL out x plus h. And so we had an x squared term, and then 2xh, and then an h squared term. And the h squared term ended up disappearing when we took the limit. So it's the same. This is like the h squared term. There are little things. This is a big thing. That's x squared. This is x squared times a little h, not this h, but the h from the difference quotient. And this is like an h squared term that would disappear when you took the limit. So we could sort of do this more carefully with algebra, but I'm quite convinced it would not be a good use of class time. So the book does a more careful derivation of this, and I'm happy to go through it. It's a handful of lines of algebra. But I think the main thing to think about with the product rule is, OK, so you see this, and you really want it to be just g primed, h primed. Just take derivatives. You're a derivative-taking machine now. But you have to stop and say, oh, no, wait. It's a sort of funny thing where it's like my candy shop is doing better because like this is the increase in cost per candy times the amount that I'm selling. And then this is the increase in the amount I'm selling times the cost I'm selling at. There are those, like, you're getting more of it for these two different reasons that correspond to these two rectangles geometrically, that correspond to those two things in terms of your candy shop. All right. So let me do one example with this, and then you'll do a bunch of examples. How about that? And you'll get the hang of this pretty quick. All right. So let me make sure I don't inadvertently do an example I'm about to have you do. What should we do? All right. F of x is OK. So here's a derivative, and we need to use a product rule because it's the product of two functions. It's one function, 2x to the 8, times another function, 4 to the x. So f prime of x. I'm using the product rule. So I've got two functions, the first one and the second one. The first one being the one that comes first. The second one is the one that's after the first one. So what this says is I wrote it in the way that's opposite of the way I normally say it. So let me Right, so there's the product rule written in a slightly different order. So this says you take the derivative of the first.
Does it really matter?
It doesn't really matter, but like the rhythm that I always talk to myself in is this way. You might get a rhythm that way, but anyway, the rhythm I hear is like take the derivative of the first one, leave the second one alone, plus leave the first one alone, take the derivative of the second one. And somebody, I remember on the first day of class, talked about a math teacher with an Eastern European accent. I can't remember who that was. It wasn't a good thing. Maybe they're off looking at right whales today. I can't remember. Anyway, somebody mentioned that as a scarring experience. Anyway, I had a German math teacher in high school who was fantastic, and I still like hear his voice in my head. He would say, "Fix this one, do that one, fix this one." Fix meaning like keep unchanged. Anyway, so you'll get your own way in whatever accent you want to hear in your head of talking yourself to do this. All right, so let's do this. So the derivative of this, I leave the 2 alone, take the 8 down. So I took the derivative of the first one, I leave the second one alone. That's one of those rectangles. Then I got to leave the first one alone and take the derivative of the second one. That's an exponential, so it's that. And that's a product rule. That's it. You will be experts at it in 10 to 15 minutes if you aren't already. So let's practice this and then see what happens. Here you go. All right. So let's go through these. We'll definitely bump into a few things we'll want to talk about, I think. So this isn't the power rule yet, or the product rule, excuse me. This is just kind of getting you warmed up. So take the derivative of this, plus the derivative of that, plus the derivative of that. Derivative of 13 is 0. How does 13 depend on x? It doesn't, so it's 0. Then the moment you've all been waiting for, now I get to use a product rule. So I take the derivative of the first one, leaving the second one alone, plus leave the first one alone, take the derivative of the second. And so product rule, it's not particularly difficult to apply. You do get large answers. Sometimes they simplify down, often they don't. Either is fine. Let's see. Here's a product rule again. I don't know why I didn't do this one. So take the derivative of the first one, leave the second one alone, then leave the first one alone, take the derivative of the second one. So again, you'll sort of get a meter and a rhythm to these as you do a bunch of them. Note that the derivative of e to the x is e to the x, so it looks like you didn't do anything, but you actually did. We good? We're OK so far? All right. D is a little messy. I always like to turn square roots into fractional exponents, because then you can use a power rule more easily. You could, and I was tempted to, multiply this out. Or you could just, it's a product. You could take the user product rule here. I decided to do that, and I got this. If you decided to simplify a little bit further by distributing this x to the half, I don't think it would end up being about the same amount of work. Often it's to your advantage to simplify first. In this case, I think it's about the same. And as you can probably guess, depending on what one does with these terms, particularly if you're looking to check your work in the back of the book, be aware that sometimes the book simplifies things a lot, and sometimes it doesn't. So if you have an answer that doesn't match the one in the back of the book, it may mean you did something wrong, or it may mean you simplified differently in the book. Just something to be on your toes about. People OK with this one? OK. So what did people say about this one? Sorry, what? The same answer? What type of function is this? What's an exponent? But it's not, like, what am I trying to say? It's not a product of two functions. It's a sequence of functions. So you start with x, you square root it, and then you exponentiate it. which is different than a function like this that like has two different functions that are done separately and then are multiplied together. So this, again, the answer to this is, huh? Right, so we don't know how to do that one yet. Yeah. You'll know how to do it soon, but not quite yet. All right. All right, so let's do number 2, just for fun. So we've got a function like x to the 7. And you've known for a long time how to take this derivative. It's the power rule. So you take 7, bring it down, and you get that. If you wanted to, which there wouldn't really be any reason to other than just to, because someone told you to or you were curious, you could say, you know what, x to the 7 is actually this. X to the 3, x to the 4. So what if I did the product rule to this? All right, so I take the derivative of the first one, leave the second one alone, plus leave the first one alone, take the derivative of the second one. And what do you know? This is 3x to the 6 plus 4x to the 6, which is 7x to the 6. So math has this pleasing internal consistency to it. So if you do something 2 different ways, you get the same answer. Whereas in all other fields, if you do things 2 different ways, you get different answers, and then you have to like fight about it, or have a discussion, or get all the stakeholders at the table. Here, different methods, I guess as long as they're correct, give you the same correct answer. So anyway, we're building up all of these rules, and periodically it's useful to do things like this to see that this edifice really is all internally consistent. All right, so that's the product rule. So that's section 3.3, chapter 3.3 from the book. And like, I could even write this down here, might as well. Derivative of fg is f prime g plus f t primed. So that's a nice rule. There's a formula for it. It's not that hard to apply the formula. You do it a few times. You don't have to memorize it. It'll stick in your head. So now let's go to 3.4, where we're going to learn how to deal with things like this. So we won't have to go, huh? We'll be able to actually do these. So let's see. Let me clear a little space. All right. So this is 3.4. The chain rule. So I spent a little bit of time last night and a good bit of time this morning trying to think of a not confusing way to present this. And what I decided is that there is no such way. So I think, and this happens every time that I teach a chain rule, it's going to be confusing for a little while. And you're not going to be happy about it. But by the time Monday comes around, it'll all be fine again. So the chain rule is a little different than these formulas here, where it's just like, here's a formula. It's just that sort of obedience test. As long as you're careful, you just kind of churn through them. The chain rule is a little harder to think about. But you'll all do fine. I've taught this many times before. Everybody does fine. But it's not something that you just nod along all the way, every step. So it's going to be confusing for a little bit until we do a bunch of examples. And even then, it'll be a little confusing. But again, eventually, it's going to be OK. And I think, unlike the product rule, where I tried to give some story and justification, I sort of feel, and then said, oh, OK, here it is, and here's how you do it. For the chain rule, I think it might be easier to do actually sort of the opposite. So talk about what the rule is and how to use it. And then in the process of using it, you'll come to maybe see why it should be true. We'll give it a shot. So as with the last one, I'm going to probably talk for 10, 15 minutes. And then we'll get to some examples, and we'll probably need to talk about those, and it'll be a little bumpy, and you're going to leave here not really believing me that the chain rule is going to be OK. But it is going to be OK next week. All right. So the chain rule. What is the chain rule even about? It's about compound functions. So if we have like y. OK. So it applies to things like this, where we have a chain, a sequence of functions. And so this, right, we go inside out. You start with x, you put x in, x gets g'd, g of x gets f'd. Right? So it's a chain of things. Here you start with x, it gets square rooted, then it gets exponentiated. So a compound function or a function of functions. All right, so here's another way. Think about this. There's an inner function. Right, there's an inner function and an outer function. The inner function is g. The outer function is f. I'm going to call the inner function z for a moment. And then z equals g of x. And this is the same notation the book uses, so at least notational confusion should be minimal. All right. So y depends on z, but z depends on x. And so we want to know, OK, how does y depend on x? Well, there's this chain we have to go through. Y depends on z, and z depends on x. So we could write that dy, dz, dz, dx. So this says that whatever this is, it's going to be the product of two derivatives. It's how y depends on z. It's how z depends on x. And we multiply those two rates together, and you can sort of picture these things canceling. And that says dy dx equals dy dx, which surely is true. All right. So now let's think about how to put this into practice. So let me write another. OK, so this is the chain rule. Let me write another way of thinking about the chain rule. I'll write another formula, and then I'll write some sentences. And the sentences are actually, I think, going to be the key to actually using this. So let me write a bunch of stuff and then talk about it. So we've got dx of f g of x. OK. All right, so let's see. So let's just start with handwriting issues. This says derivative of outer function, pretending inner function is constant. This asterisk is to indicate multiplication. And then this says derivative of inner function. So this word equation and this equation and this equation are all saying the same thing in different notation. And when you're actually using the chain rule, I think it's this word equation that you want to sort of have in your head conceptually. And so when I do the chain rule, I don't really picture these formulas at all, even though that's what I'm using. So let's do an example, and let me make sure I'm not about to do one of your problems for you. OK. OK, so here's an example. Y is x squared plus 2, whole thing raised to the 3/2 power. So this is a compound function. We start with x, we square it and add 2. Then that whole thing gets raised to the 3/2 power. So it's a chain of things that's happening. And so we want to take the derivative. So the outer function is blah to the 3/2. So it's something to the 3/2. So what's the derivative of blah to the 3/2? 3/2 blah, here's blah, to the half. Yep. Then I need to take the derivative of the inner function. The inner function, formerly known as blah, is x squared plus 2. Derivative of x squared plus 2 is 2x. Yep. So that's the chain rule. You can't really do much more with this, because this is like this half is a square root. It would be, I mean, I guess you could technically bring in some, but I would leave it alone at this point. Yep. Should I do another example, or are you just?
Yeah.
OK. I thought so. I just thought I'd check. All right, let's see. I guess we might as well, to achieve some closure, why don't we deal with this one? Whoops, sorry, that's y. So e to the square root x. We want to know what that is. Maybe it might help to write that as e to the x to the half. Since exponents are almost always easier to work with than radicals. So what's the inner function and what's the outer function here? What happens first to x as it undergoes this journey? Yeah, so first it gets power halved, and then it gets exponentiated, e to the d, or I don't know even how to say that. So the outer function is e to the blah, where blah is shorthand for the inner function. So over here I called blah z, but everybody just calls it blah. Really. You know how MIT has their all their lectures online? They say blah. Everybody says blah. I saw one guy that said blap once. That seems I don't know. I didn't like how that sounded. Most people call it blah. I mean, you could call it z, but everybody calls it blah. So just some sort of placeholder. So the derivative of e to the blah is? E to the blah. Yep, that's awesome because it's its own derivative. Oh, but then I need to take the derivative of blah. So that would be, you could do this in steps if you wanted. So that's the derivative of the outer function, pretending the inner function is just blah. And then I need to take the derivative of the inner function. The inner function is the thing formerly known as blah. And so outer function, don't worry about the inner function, multiplied by the derivative of the inner function. So at this point, I think we should just go for it with some examples. Yeah. If there was a 3, it would 3 just hangs out. Yep. All right, so let's give these a try, and we'll probably pause a couple times and talk about them. All right, let's, having walked around the room, people seem to be almost uniformly distributed throughout the worksheet in terms of where people are right now. So not knowing what else to do, I thought, well, let me say a few things and then spend another time working on this. So first, let's do the first set of ones. So here's e to the 3x. So the inner function is 3x. The outer function is e to the. So the derivative of e to the blah is e to the blah. The derivative of 3x is 3. Here's another way to think about the chain rule. So how does the function e to the 3x compare to the function e to the x? Or in general, how is this function related to that? This is when people you should start gesturing at me. Stretch, or then, OK, so there's also, so one of these is going to stretch. One of these does the compression. So this one lives its life 3 times as fast. It's just sort of another way of thinking of it. So if you compress something in, what's going to happen if you compress this in by 3? What would happen to the slope? It's going to be steeper by 3. So you're living your life 3 times as fast. So the roller coaster of your life is 3 times as steep as a roller coaster of somebody living at normal speed. So this one, the derivative is going to be, and this is exactly what we saw, right? The derivative, taking the chain rule kicks out this 3. That's 3 because you're living 3 times as fast. You could also, like this one is, you're living, all right, I'm not sure where this metaphor is going, but you're living like 3 times as hard. Meaning your lows are 3. All right, so like, we haven't talked about derivatives of sine waves yet. But here would be a basic, here's like, all right, so this is f of x. You could live 3 times as hard. So the point is, like, this purple line is 3 times higher. And so the steepness of this is 3 times what it was before, because your highs are higher and your lows are lower. You could also stay within these limits, but just do everything 3 times as fast as everybody. And now this graph's really going to look like a mess. Oh, boy. 1, 2, 3, 1, 2, 3. All right. So now your derivative is 3 times larger because you're going 3 times as fast, not because you're 3 times as high or 3 times as low. Anyway, so the geometric work we did in way back in 1.3, the chapter that I really liked, and you're like, it's all right. This is where some of the payoff is. If you can kind of think of functions in that way, these rules just sort of fall out from that geometry. OK, so this one. All right, so this one's living life 3 times as fast. This one is living life 3 times as fast and 3 times as hard. So we get a 9 here, 3 times 3. All right, let's see. This is not the chain rule, but your old friend, the product rule, that you met about an hour ago. So derivative of the first one, leave the second one alone, plus leave the first one alone, take the derivative of the second one. You've already got that meter down. Here's the chain rule. There's an inner and outer function. Derivative of e to the blah is e to the blah. Derivative of blah is 3x squared.
But don't you have to leave, like, do the derivative of the outer function, and you you write the blah part that didn't change and the derivative of blah. Shouldn't it be?
Yeah. Yeah, so this is, maybe it would be, right, I guess it might have been better. Let's say the problem instead was, what was that, e to the x? Let's say that's like 4 to the x cubed. Then the derivative of 4 to the blah is log 4 to the blah. So this example might be better because you can't see when you took the derivative of e to the blah. Because the derivative of e to the blah is e to the blah. That's why e is so awesome, this natural pure number. So maybe this makes it a little more visible what's going on. The flip side is you would have been writing more. Let's see. So this is product and chain rule. Exciting. So derivative of the first one, leave the second one alone. Leave the first one alone, take the derivative of the second one. Again, the answers for derivatives are usually larger than what you started with. It's rare that taking derivative makes things more compact. And here, this is just a derivative plus a derivative. Questions on these? My sense is this is going as well or better than I would imagine. So if you're feeling like, oh, okay, maybe, but you're not 100% there yet, that's sort of that's perfect. That's where I'm hoping people are. Like, maybe this is all right. That's where I'm hoping to get. All right. So let's talk about the first word problem, and then I'll stop talking for a few minutes, and you can do the second word problem and the few other examples. And can I steal somebody's sheet back? Thank you. All right. So here I've got the length L of a metal rod, and the length depends on temperature. But temperature might depend on time. But we want to know how length depends on time. So, all right, so what we're given, length increases by 2.5 centimeters for every degree in temperature. So 2.5 centimeters per degree. What would that be in terms of L's and temperatures? So that 2.5 be, that's a bad C. So that tells you how L depends on T, capital T, temperature. And then what else do we know? We know temperature is increasing at 4 degrees per hour. What sort of quantity would that be? That's what over what? It's temp over time. And so then, thanks, Omar, we can should probably put a C there. You can just sort of see if you multiply these two things together, the temperatures cancel out, and you're going to be left with centimeters per hour. So 2.5 centimeters degree, 4 degrees per hour, 10. Two times 4 is 8. Yeah, I think that's 10. So the length depends on temperature. When you heat it up, it expands. And the temperature depends on time. Temperature changes as time changes. If we want to know how the length of the metal rod changes with time, well, we've got this chain of relationships. L depends on time indirectly because L depends on temperature, and temperature depends on time. And again, this isn't a proof of the chain rule, but if you sort of think about it in a physical situation, you think about units, it seems like the plausible thing to do. All right, so let's continue along this line of plausibility. If you haven't already, try the second word problem, and maybe then the last couple calculations, and then we'll let the dust settle. 10 minutes left. Let's talk through number 3, which is a little trickier than the metal rod example we just did, and then maybe we'll do A and B, and skip C in the interest of time. So now we have, I've forgotten what the situation is. This is it's an oil slick. Okay, oil slick is growing. All right, yeah, I guess these kilometers. It would have been more interesting to do a growing piece of pizza. That'd be much happier. But it's hard to. So this could be a 7-kilometer pizza that's growing at this rate. That's better news probably than the oil slick. So we know area as a function of radius. It's our old friend pi r squared. And we can calculate how area depends on radius. And it's 2 pi r. But what we're interested in this problem is how area depends on time. Right, so we want to know dA dt equals. And a good strategy for these, and I heard Corey saying this as well, is to start by writing down the stuff you know. Because these are often ones you need to kind of piece the puzzle together. So we're told, OK, something blah, 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 0.1 kilometers per hour. That's how fast the radius of the pizza or oil slick is changing. So kilometers per hour, again, thinking about units and derivatives, that's going to be a dr and a dt. And then, all right, you know the formula for the area of a circle. How that depends on r is this. And now we can use the chain rule. Every time I want to use this form of the chain rule, I've just erased this form of the chain rule. But anyway, I want to say that area depends on time. Why? Because area depends on the radius, and it's the radius that depends on time. So that's sort of the chain out this set of relationships. So let's see, I'll write that here. Area depends on time because area depends on the radius, and the radius depends on time. And you can see the dr is cancel. So in a sense, this is saying that dA dt is dA dt, which is comforting to suggest that you have these things sort of in the right order. So now we can just sort of plug in. Oh, I have an expression for dA dr. That's just 2 pi r. And what's dr dt? I don't have a formula, but I have a number for that. That'll work. This is 0.1 kilometers per hour. And note that we need to know r. So this says that the larger r is, the faster the area is increasing. And we've talked about that before. Like if you have a 5-inch pizza and you go up to 6 inches, you're like, more pizza. But if you're at a 6-inch pizza, you go to 7 inches, you're like, wow, even more pizza, right? Because right. So same sort of thing. That's what this r is doing here. Bigger r, more. I was going to say bigger r, more pizza. The more pizza is more pizza. Anyway. Okay. 2 pi 7 kilometers, 0.1 kilometers per hour is going to be, I don't know, 1.4 pi 6-ish. Might as well get a number out of this. Lexi's on it. Okay. All right. Emily's on it. Okay. You've got backup.
Oh no, I was not
Okay.
Is it 4.30?
Yeah, 4.39. Yeah.
All right. Okay, so this is how fast the oil slick is growing at this particular moment in time when R happens to be 7. All right. Since I've started them, and I know some people have gotten to these, let me go through these quickly and then, like, say a minute or less of concluding remarks. So this is blah to the half. Derivative of blah to the half is half blah to the minus half. Then I need to take the derivative of blah. That's 1 plus x cubed. The derivative of 1 plus x cubed is 3x squared. So now that tells me how fast the function is changing as a function of x. And we could always, if we want to know how fast it's changing at a particular x, what the slope of this funny thing is when x is 3, well, we don't have to do any difference quotients or anything. We just plug in 3. And I think I've managed to choose numbers that are not going to be pleasant. It's going to be 27 halves over the square root of 10, I think. And you can evaluate that on a calculator. The point is, you can plug in a number, evaluate it on a calculator, and you get a number for the slope. You've just exactly calculated the slope of a curve, something that seemed forbidden a while back. And I think this one isn't a chain rule. Well, I've gone this far. All right, this is 1 plus 2z. If I plug in 1 here, I get 3. If I plug in 3 here, I get 5. So the derivative is increasing. What does that mean the second derivative is doing? 7. Oh, that's 7? Yeah, OK. Because 2 times 3 is 6. That's what tripped me up there. All right. So the derivative is increasing. What does that mean about the second derivative? Positive. So the concavity is? Yeah. So this, what is this going to look like? It's going to look something like that. So it's getting steeper all the time. And I know that just because this is like a parabola sort of thing. Anyway, so the point is, we've got all these rules and the chain rule, and you can get lost in letters. But every now and again, it's good to come up for air and remind ourselves like that these numbers have meaning. So yes, the slopes are increasing. It's a parabola. So as I said, I'm hoping people are at the point where you're maybe like guardedly optimistic. You can imagine a day when the chain rule is your friend, but you're not quite sure you're there yet. So that's all right. That's what the next class will be about. We'll do a lot more practice. Chain rule is super important. It takes a little while to get the hang of it, but you'll all be fine.